Hello, my name is Marco Arruda and welcome to the third part of the series Exploring ROS with a two-wheeled robot. So, if you have been following this series, you know already what we are working with. If that's the first time, that's the first video of the series you are watching, I recommend you to start watching from the first video and then get to the part we are working with. So for the video of today, we are gonna work with the same robot, so a two-wheeled robot, and we are gonna put a new sensor to this robot. We are gonna work with a laser scanner. So in order to keep working with our project, we are gonna work with RDS, ROS Development Studio, provided by the Construct. So I have an account already, so I'm just gonna make the sign in. If you are a new user, you can do the sign up clicking here on this link. So I just need to fill my email and password, sign in, and after the sign in or sign up process, you may be able to see this page. If you don't have the project here created, we are going to start from our repository. Okay, so we have this repository, two-wheeled robot, inside the Construct account. This is a public project, and we are going to clone the repository from the second part. Okay, so we have only 2 commits here. Let's clone it to a new project. So go to RDS, create a new project. Let's name it third part. And the description, I'm gonna put the same, doesn't matter. Create project, and okay, it's ready. Let's open the project and wait a few seconds until we have the environment ready to be used. Okay, great. I don't want to restore the previous workspace I was working. So let's start cloning the repository to the simulation workspace. For this reason, I'm opening a new shell. This is one of the tools we have available in RDS, and you can see on this left bar here the windows you have opened in your RDS desktop. Okay, so first of all, we have 3 folders here: Catkin Workspace for ROS applications, we have the Notebook Workspace for Jupyter files, and Simulation Workspace for simulation packages, also a ROS workspace. So let's get into Simulation Workspace source folder, and we have nothing here, so let's clone the repository. Okay, here we have the files. Let's compile it. Actually, we don't have any C++ files, but I'm compiling just to generate the header files, the same files that are going to allows me to use the auto-completion inside the shell, for example. Let's wait a few seconds. In the meantime, we can open the IDE here, Tools, Cloud9, that's the IDE we are using, and you can check inside the simulation workspace. We have the package my two-wheeled robot description. Okay, so here we have, and so our main goal is to insert the laser scanner sensor to the robot. Okay, so let's start checking the robot we have from the part we have stopped in the last video. In order to do that, I'm gonna launch my two-wheeled robot description package. We have this RVis launch. RVis is the robot visualization tool provided by ROS, and in order to see RVis, we have this graphical tools application here. Okay, so open the graphical tools, and you are going to see the RVis application running. Let's put it bigger. And add the robot visualization here. It's called, you can just click here and type robot state. wait a few seconds until RVS generates the robot visualization. And here we have, so this is just a two-wheeled robot. And let's start working to add the sensor, okay? So I have defined actually two main steps to add the sensor. The first step is to create a new element inside the URDF definition. So we have 4 files. The main file is the my two-wheeled robot chakra file. Here we have all the links of the robot defined. So we have the chassis and the two wheels, followed by their joints, okay? And we're going to create a new link here. So for my sensor, I just want to add the sensor right here in the front of the robot, okay? So just a cylinder would represent the sensor for me. That's why I'm gonna create a link as simple as a cylinder, just to represent the laser scanner, okay? I'm gonna copy and paste here the link I have already in another file. So here we have, just to not waste your time, and let's take a look line by line what we are creating here in our robot. So basically we are creating a new link. If you still have doubts about what is a link and what is a joint, you can watch the previous videos of the series, and also this material from ROS. You can see here, you can find this link at the description of the video. There's a page describing the links and all the properties you can use for the links, and also another page documenting the joint elements, okay? So let's get back to the source code. And here we have basically this new link, sensor laser. We have the inertial group of properties. We are defining the origin of the link. We have 0 for all the origin, okay? Because I'm gonna move the position of this link using the joint later, okay? We have the mass. I put here just 1 because this is a good value, and actually it's not gonna interfere a lot in the robot, okay? And finally, I'm using here a macro. We have explained about macros in the previous video, so you can check there what is a macro if you don't know yet. So I have created this macro here, okay? And we are going to put it inside our macros file. This is basically just creating the inertia tensor for a cylinder, okay? Because I don't wanna calculate it every time that I create an element like this. That's why I'm using this macro, okay? You can check here, we have in the link chassis the same definition here for the inertia, but we are not using a macro. But for this time we are going to use, just to save some time and show how you can do it more effectively, okay? So we have to define this cylinder inertia in the macros file. Let's open it, and I'm gonna just copy and paste, and we can see what's being done here. So we have this macro called cylinder inertia, and we are receiving the mass, the radius, and the length as parameters, and inside the macro we are defining the properties and doing some math here, okay? This is basically just the formula we are applying. No big deal for robotics, just usual stuff, okay? Let's save the file and get back to the sensor link. So finally we have the visual, the origin the same, just 0. For the geometry, the same cylinder, the same properties we're using to calculate the matrix here, okay? And defining the color, so why it's good just to see a different color in our robot as a sensor. And for the collision, just the same geometry, a cylinder, the same radius and length, okay? So now we have created this. Now we have to create a joint, because we cannot just have another root link. A root link is a link that is not binded to a parent link, and the only link we have like this here in this robot is the link chases. Okay, so we have to create a joint to bind this link to the link chases, and this is exactly what we are doing here. So a new joint, I'm calling it joint sensor laser, and the type of the joint is fixed. Okay, you can take a look here why I'm using this kind of joint. So a fixed joint is not really a joint because it can move, it cannot move. Okay, and this is exactly what I want, what I need. Okay, I don't want my sensor to move in relation to the robot, to the rest of the robot. Okay, and we also don't need all these properties here when we are using a fixed joint. Okay, what makes our life easier for this case. So the parent link is the link chases, the child link sensor laser, and here origin of the joint. I am defining the position of the sensor in relation to the chases. Okay, and no rotation for the laser. It's enough for me. Okay, and now we have defined the new element, just creating a new link and a new joint, and also taking the opportunity to create a new macro and show just another example of macros and how this can make your life easier working with URDF and chakra files. So let's restart RVs just to see the new element we have just created. Just use Ctrl+C here and run it again. Okay, so let's insert the robot again. Robot state, and there it is. We have this white piece which represents our sensor. Okay, this is exactly what I need, just to show a new part of the robot as a sensor. So now we have this ready. We can visualize the sensor of the robot here in RVs. So let's go to Gazebo. I think it's important to explain that RVs is not a simulator. Okay, what we have here is just a visualization tool. So there are no dynamics running in the background of RVs. Okay, we are just visualizing the robot, and you can visualize a lot of data from robotics. Okay, using the RVs tool. It's a very useful tool, but it's not a simulator. That's why we have a launch file here for Gazebo. I'm sorry, for RVs, and another launch file for Gazebo, which is the spawn launch file, we just spawns the robot to a simulation. Okay, so we can just close RVs now. And before running Gazebo and see the robot in Gazebo, let's create, let's go to the second step of putting a sensor to in the robot, which is assign a Gazebo plugin to that link. Okay, basically a Gazebo plugin just assign a sensor behavior to a specific link. In this case, the specific link is the sensor laser, and we want to assign to this link the behavior of a laser scanner. Okay, and we have actually a Gazebo plugin for the purpose. You can check here in this page. You can also find the link to this page in the description of this video. Okay, and basically you have here a very good explanation and a list of the Gazebo plugins available for ROS. Okay, in our case we are going to use the laser, and which is basically using that notation here to put a new laser. So I have done some modifications for this example. I'm gonna just, let's get back to our source code. I'm just copy and paste the plugin and then I'm gonna explain what we are doing line by line. So let's open the URDF Gazebo file. We have already some notations here. We are defining some colors for the robot, and we have also the plugin of the differential drive controller to send velocity commands to the robot. And now let's insert the plugin of the laser. So let's start here the first line. We are defining this plugin, and the reference is the link sensor laser. Okay, the kind of sensor is ray. It's defined here in the Gazebo page, and the name, I'm calling it head Hokuyo sensor just because I have copied from here. And the pose, you can just use 0 because you have the pose defined already in the link here in this chakra file. Okay, visualize. If you put it to true, you are going to see the rays of the laser in the simulation. We are not interested to see it. Here is the update rate of the data. 20 is enough for us for this example. Now some properties of the ray. So basically we are scanning in the horizontal. Okay, we are getting 720 samples, and the resolution is 1, and that's the mean angle and max angle we are working with. So we have from minus half of p to half of p. So we have half of a circle as the range of the laser scanner. Okay, and the range of the laser, the max distance the laser can reach is 10 meters, and that's the minimum. Okay, and the resolution of the data. Finally, the noise. We are defining here a Gaussian noise. That's the mean and the standard deviation. Actually, this is not so important right now. Of course, this is important if you are working with filters, but not for this example, because we just want to show how you can put the sensor to the robot. But for instance, the noise of the sensor is not important, for instance. Okay, depends the application you are working with. And finally, at the end of the plugin, we define this plugin attribute. We have to use the exactly same name, so Gazebo ROS head Hokuyo controller, and the file name libgazebo ROS laser so. Okay, here I'm defining the name of the topic. The data from the simulator is going to be published, so I'm defining my two-lead robot laser scan, and the frame name, I'm creating a new frame called sensor laser. Okay, so make sure the file is saved, and let's spawn the robot. Actually, let's start a simulation. Just an empty scene is enough for us. Let's wait a few seconds until we have the simulation ready. And have the terminal here on the left side. You can now close the graphical tools. We're not going to use it anymore. Okay, so it seems the simulation is ready. Now let's launch the robot. So ROS launch my two-wheeled robot, description, spawn, launch file, and the robot shall appear right here in the center of the world. Let's take a look in the log of the simulation. Oops. Okay, so here it is. Here we have the robot. Here we have the laser element. Let's check if we have the laser in our topic list. So ROS topic list. And here we have my two-wheeled robot laser scan. Okay, let's check ROS topic HC, my two-wheeled robot, laser scan. So we have messages being published at this frequency. Great, this is what we need. Now let's check RVs again. So ROS run, ROS launch, my two-wheeled robot description, RVs, launch file, open the graphical tools. And now we can add a new visualization tool, which is laser scan. Okay. The fixed frame, let's select Odon frame. And the laser scanner, we have to select the topic which the messages comes from. So that's the topic, my two-wheeled robot, laser scan. You can also add the robot state just to see the robot and compare the robot to the laser information. So here we have the robot. Let's get back to the simulation because we cannot see the laser information yet. So let's get back to Gazebo and insert some elements here in the world. Let's put some boxes around the robot. And we can check if the laser is detecting these obstacles. Okay, so let's go to this position more or less and try to reach the same position in RVs. And here it is. So using RVs we can check the laser scanner. So you can see we have more or less the same. We are looking at the robot more or less at the same position, so you can check here we have the boxes around the robot using the laser scanner. Okay, so that's it for this video. I hope you liked it. I hope it can help you to work with ROS, Gazebo and sensors, in this case laser scanner. And don't forget, if you like this kind of video, please subscribe to our channel, press the bell to be notified about the videos that we publish every day. Thank you.